who's coming from TTL.
Thanks, Jelani. Thanks to the organizers for inviting me to give a talk at this workshop. So today I'll be talking about our joint works on sketching algorithms for maximum directed cut and other CSPs. So my main focus will be on this max directed cut problem, and I'll briefly try to sketch our algorithms for general CSPs as well. Right, let's get started. Here's the talk outline. First, I'll go over the problem definition and folklore algorithms. And the main bulk of the talk will be on sketching algorithms for Max-DICUT and the related lower bounds. And then if there's time, I'll also talk about generalizations for arbitrary CSPs. And finally, I'll conclude with some open questions. Let's get started. So let me first define a closely related CSP, which I'm hoping we all are familiar with, which is the Max-DICUT problem. Here we are given an undirected graph, and the task is to find a bipartition that maximizes the number of edges that go across the two sets. For example, in this case, this bipartition that I just drew here is the optimal bipartition, and the cut size is 4. And this is called the max cut size. Max-directed cut is a related problem where instead of an undirected graph, you're given a directed graph. Again, you want a bipartition, but this time you want to maximize the edges that go from, let's say, a left set to the right set. There is a notion of direction even in the partition. And in this example, this is the optimal partition, and the die cut size is 3. Okay, so what are constraint satisfaction problems in general? So this is like a very broad definition that captures problems like max-cut, max-directed cut, which I defined above, and also lots of other optimization problems. Okay, let's just see what the general structure is. So you have like n variables, and you have some finite number of constraint types you can apply on these variables. In this example, let's say that you have like 2 constraint types, and each is of arity k. And what is meant by arity is just that how many variables each constraint applies on. And there is also a sense of direction, like in the directed graph, like each constraint, the edge corresponds to a constraint, and it says that here's the here's the in vertex and the out vertex. Something like that. You can think about constraints as being directed. And let's say, for example, like this in this instance, the red constraint apply on these 3 variables, blue constraint applies like this, and another red constraint. Let's say this is the instance. Now, the goal is to maximize the number of constraints satisfied by finding some partition of the vertex set. So the constraints are going to be in such a way that for particular assignment of these variables, or for them being in a particular partition, whether they are satisfied or not, that's how it's decided. For example, let's say that the red constraint says that if your last variable is yellow, then the red constraint is satisfied, and the blue constraint, maybe it's like the variables must be like yellow, pink, and orange, only then the blue constraint is satisfied. So in this particular example, if we consider this partition that I drew, where we are placing these 3 vertices in the orange set, this vertex in the yellow set, these 2 vertices in the pink set, then the first constraint, the red constraint, is going to be satisfied, and the blue constraint is satisfied. But this third constraint won't be satisfied because this property is not true. And we can see that this is actually the best possible partition, and you can only at the most satisfy 2 constraints at a time in this particular instance. So we would say that the value of this instance is 2 because that's the maximum number of constraints you can satisfy. All right. So for most constraint satisfaction problems, exact computation is hard. Okay. Before that, why are we even like interested in studying CSPs? So the general structure allows us to study infinitely many problems simultaneously. This broad definition like also captures interesting problems like unit games, max, k-sat, k-and, like many interesting problems. And it also allows for like finite classifications through so-called dichotomy theorems. And there are like several works that study such dichotomy theorems. And in turn, this has led to discovery of new techniques that are broadly applicable. For example, STP rounding, sum of squares, unit games, all this originated from the study of CSPs. And in turn, this helps us understand the power and limitations of algorithms as a whole. And why do we want to study Max-DICUT in the streaming setting? So to me, the first reason is that it's just the simplest problem with non-trivial approximability in the streaming setting. And we'll shortly see what that means. And we also were able to generalize the streaming algorithms and lower bounds for Max-DICUT to arbitrary CSPs. The hope is that if we study optimal algorithms and lower bounds for Max-DICUT, hopefully we can lift it to all CSPs and thus obtaining very general algorithms, and which is why my interest is on studying Max-DICUT and then work on generalizations to arbitrary CSPs. Okay. So this is what I was alluding to earlier. Exact computation of the optimum value is going to be hard for most CSPs. So we are interested in approximation algorithms. And let me define what an alpha approximation algorithm is. So for a parameter alpha, the alpha approximation algorithm is one that outputs a value that's between alpha times optimum and optimum. So if you notice that I'm not asking for the optimal assignment itself, but I'm asking only to output a value that approximates the optimal value, not asking for an assignment that has this corresponding value. And the reason is because in streaming setting, you don't really have enough space to even like output your assignment typically. So we are not even going to that goal. We're just asking for you to output the value of the CSP instance and not for the assignment itself, which is good. Okay. And you can think about an alpha approximation as an underestimate that's not off by a factor more than alpha. And this is the definition for a deterministic algorithm. In case of a randomized algorithm, we just want to output such an estimate with probability, let's say, at least 2/3. Okay. It is also typical to study approximability of CSPs through the lens of promise problems. And what are these promise problems? So for every parameter like beta less than gamma, you want to answer this question. Can you distinguish instances with value at least gamma from instances with value at most beta? So I give you this promise that it's either this or that. Can you actually distinguish these instances? Why are we interested in this notion? The idea is that if you're able to answer this question for the entire range of like beta gamma, that's actually stronger and a finer notion of approximation corresponding to the previous one that I talked about. For example, if from this I want to conclude like what's the best possible approximation, I'll do exactly this. Like I look at all indistinguishable pairs gamma beta, and if I look at the ratio beta over gamma, that actually gives me like the optimal alpha approximation algorithm that I defined earlier. And you can think about this in terms of the approximability curve, where for every beta you plot the gamma, which is like the largest gamma that's indistinguishable from it, and then you just look at the ratio beta over gamma and take the infimum. And that's sort of this approximability curve is what we want to understand for CSPs in general. Any questions? Okay, so what are some of the folklore approximations? So for Max-DICUT, just a random cut achieves half approximation. So if you're just trying to output a value, just outputting the number half gives you a half approximation for Max-DICUT. So random DICUT, again, achieves 1/4 approximation. And similarly, just outputting 1/4 gives you 1/4 approximation. Now, you can also obtain 1 minus epsilon approximation this way, where you just like randomly sparsify your graph, or in other words, you just sample order n like random edges, and if you compute the Max-DICUT or DICUT value, or in general, like even max CSP value, then that helps you get 1 minus epsilon approximation. So these are some of the folklore approximations for CSPs. And now, what are we doing in the streaming setting? In the streaming setting, it's that the edges arrive one by one in the stream, and then in the end, you're asked to compute the size of the largest, in this case, largest DICUT. And that's the idea is that you don't have space to store all your edges. You have very limited space, sublinear space. Now, what kind of good approximations can you get for the size of the largest DICUT? Okay, so now I'll talk about the state of the art we know for Max-DICUT, and then jump into details of all these algorithms. So let's look at, for the single pass algorithms, the state of art for Max-DICUT. If you plot all the algorithms that I just discussed so far, so here, one is just if you want to do the exact computation, you can just do an n square space, store all the edges. If you want to do 1 minus epsilon approximation, you can do in like order n space. So yeah, one more thing is like, I'm plotting space in the x-axis and ignoring like log factors and stuff. So really, you should read this as like O tilde square root of n, O tilde n, and so on. And of course, with no space, you can get 1/4 approximation, which is just that. I don't even look at the stream and just output 1/4. That gives me 1/4 approximation. Now, this is the folklore. So what's the first result that was known here? So basically, you can convert like a simple reduction helps us get from a max-cut lower bound to a max-die-cut lower bound, which says that you cannot do better than half approximation in little o of n space. So if you want to beat half approximation, you might as well do like 1 minus epsilon approximation. And this work of ours shows that there's this thing called bias-based algorithm, which gives you like some 0.44 approximation. But if you want to beat that, you cannot do it in like little o of square root of n space. And a very recent work, we show that, in fact, if you're given slightly more than square root of n space, like square root of n log square n or something like that, we can beat this 0.44 approximation and get something better. So now the most interesting open question in this area is like getting a deeper understanding of the approximability in this space. Like right now we have no clue, like if there is a nice space versus approximability trade-off or anything like that. So that's sort of like the biggest open question now, understanding this space. Okay. Now let's say that we consider a setting where the edges actually arrive randomly ordered. The graph itself is adversarial, but the order in which the edges arrive in the stream is just like they are randomly shuffled. In this case, actually, you can implement the same snapshot algorithm that we saw before in just like some polylog space. So that seems like in random ordering in just like O tilde one space, you have this algorithm that has this 0.485 approximation. And again, a max cut lower bound like a reduction from max cut lower bound shows that you cannot do better than half approximation in square root of n space. The belief is also that you can use these techniques and the techniques from the previous work that I showed in the slide to get even a stronger lower bound that shows that even in little o of n space, you can't do better than half approximation. So here, the biggest question is whether we can actually approach half approximation in O tilde one space or even little o of n space, or is there a better lower bound here? So this, again, this area is like completely, we don't understand that. And for multipass algorithms where you're allowed multiple passes over the same set of edges, the picture is still even less clearer than the previous two settings. Here, so again, the snapshot algorithm that I described before can actually be implemented in 2 passes to get 0.486 approximation. So I just want to pause here and say like why this result is actually quite surprising in the sense that if you look at the very related max cut problem, actually the belief is that even if you're given like little o of log n passes, you shouldn't be able to beat its trivial half approximation or something. But for Max-DICUT, just by giving an additional pass, you're able to beat the trivial, not trivial, the best log space approximation algorithm in single pass. So it's, oops, sorry. So it's, yeah. So that's why this is kind of interesting because it shows that for at least for Max-DICUT, even an additional pass could give you a significant gain over like single pass for this problem. So it's very interesting to understand like what happens when you have like subsequent passes. Can you approach like half approximation in like little o of n space or something? All right, so let's, for the rest of the talk, I'll talk about the best log space sketching algorithm for Max-DICUT, talk about the omega square root of n space lower bounds, and then all the recent improved approximations in square root of n space, log space random ordering, and 2 passes. And if time permits, I'll also talk about generalizations to arbitrary CSPs. Yeah.
Wait, so even for max cut, if you go below order n space, is this 0.48 thing the best? Like your algorithm implies a 0.48 something for max cut, and is that the best or?
Thanks a lot for the question. So, okay, the question is like, what is the best known for max cut in like little o of n space? So for max cut, actually, like if I just give you constant space, you get a half approximation because a random cut gives you.
Oh, right. Oh, 0.48 is worse than half. Sorry, that was a dumb question. I understand. Okay. Okay, I got it.
No worries. Yeah. So max cut, really, you can't do. It seems like you can't do anything for max cut. So that's why we are interested in studying the Max-DICUT problem. Okay. So first I'll talk about like a weaker approximation problem. And this is just that to kind of motivate what this bias-based algorithm does. And then I'll talk about the stronger 4/9 approximation. So, okay, so let's look at this 2/5 approximation algorithm. So first, what is this bias-based algorithm? So the idea is that if you look at each vertex and look at its bias, which is just the difference between its out degree and in degree, that should pretty much give you an idea of where to place the vertex. For example, if a vertex only has like edges going out of it, you should just deterministically place it in the left set. And if a vertex only has like edges coming in, you should place it in the right set. That's sort of the high level idea. And here, basically, this kind of intuition works is in the sense that if a vertex is like positively biased, place it in the left set in your partition. And if it's negatively biased, place it in the right set. And it turns out that if I just take the best of random cut and the good die cut, that gives me a 2/5 approximation. So this sounds very simple. But the thing is that if you look at it in the streaming setting, you're not going to actually able to identify which vertices are positively biased and which vertices are negatively biased because, oops. Okay. So you're not going to be able to identify which vertices are positively biased and which vertices are positively negatively biased because you're not going to be able to store all the vertices and all the bias. And also, if you recall, we're not actually asking for the optimal assignment to all the vertices. Rather, we are asking only for you to output the optimum value that you get as a result of this assignment. So now the goal is to actually compute what this die-cut value is that you achieve from best of random die-cut and good die-cut, and whether that die-cut value can be outputted in the streaming setting. So let's talk about estimation in log space, how we estimate this value. So we define a quantity called bias of the graph, which is just the L1 norm of this bias vector, which is where every component is just the bias of the vertex itself. Now, the thing that we show is that Max-DICUT value is very closely related to this bias of the graph. We give upper bounds and lower bounds in terms of this bias. And so where the lower bound comes from the fact that m over 4, if m is the number of edges in the graph, m over 4 is just what you get from a random die-cut. Bias over 2 is from good die-cut, and this is the upper bound. So if you plot this as like upper bound on Max-DICUT value in terms of bias and lower bound, then if you look at the bottleneck is like somewhere here, which gives you a 2/5 approximation between the ratio between the upper and lower bounds. So that's kind of the high-level idea. And how do we compute this bias itself? So it's clear that if you want to output the Max-DICUT value, all you need to do is compute the bias. But this is just an L1 norm of a vector that is getting updated in the stream. And so you have a log space sketch by this classic algorithm of indic, which helps you compute the bias of the graph. So now I'll talk a little bit about why these bounds hold. So for the upper bound, it's just that you have this simple thing that for every vertex, you have at most out degree or in degree edges in the die-cut incident on it. So if you place it in the left set, you lose all the edges that are incoming. And if you place it in the right set, you lose all the edges that are outgoing. So if you just account for that and do like a simple counting argument and some rearrangements, you get the upper bound that your Max-DICUT value cannot be beyond this quantity, which is 2m plus bias over 4. Okay. So for the lower bound itself, the only thing we need to show is that the good die-cut has value at least bias over 2. So this simple argument is actually due to my former advisor, Madhusudan. So the idea is that let's say you remove directed cycles from the graph. This does not change the bias because for every vertex, you lose one out edge and one in edge. So that shouldn't change the bias of the vertex and in turn the bias of the graph itself. So let's say we remove all the directed cycles and end up in a DAG. And in the resulting DAG, let's keep removing maximal paths. So if you look at a maximal path, it goes from a vertex which has it goes from a source to a sink. And this has like out degree greater than in degree, and the sink has in degree greater than out degree. So if you look at a path, there should be at least one edge such that on on the left endpoint, the out degree is like greater than in degree, and the right endpoint, the in degree is greater than out degree. In other words, it will be a good edge in the good die-cut, where the left endpoint has greater out degree and the right endpoint has greater in degree. So this shows that each such path decreases the bias by 2, but because there exists at least one edge in the good die-cut in this path, it contributes at least 1 to the value of the good die-cut. So by this argument, the good die-cut should be at least biased over 2. So because of these simple reasonings, you have this upper and lower bounds, which gives you the 2/5 approximation. Now I'll talk about the 4/9 approximation. So for the 4/9 approximation, we made this observation that if you look at graphs with small bias, instead of doing like previously we just said that we take the best of random die-cut, and for this region, 1/4 was the value that we were outputting. Instead, if you look at a slightly biased assignments, where if the vertex is positively biased, place it in the left set with some bias probability, and negatively biased with right set with some bias probability, then you can actually get a better lower bound on the max die-cut value in terms of bias. And that's what's plotted here in the red curve, and this gives us the 4/9 approximation. The surprising thing is that not just that these values don't really matter, the fact is that this is also optimal in square root of n space. And what do I mean by that? So if you look at bias, it distinguishes instances like from the bottom curve from the instances on the top curve. And this shows that in this entire range, this is optimal, in the sense that if I fix some bias, I can come up with 2 instances in streaming model such that their values match the upper and lower bound, and they are indistinguishable in the streaming setting. So what this essentially shows is that we have a dichotomy theorem, where if you look at any parameter, these kind of promise instances that we were looking at, beta less than gamma, either if you look at instances of opt at least gamma and instances of opt at most beta, either their bias values are separated, in which case you just compute the bias of the instance and you know which set it belongs to, or you don't have any streaming algorithm that correctly distinguishes in square root of n space. So what this means is that for the Max-DICUT problem, bias is like all that you can compute in little o of square root of n space, which helps you distinguish instances optimally. And this intuition actually turns out to be super helpful, because in a later work, we showed that this is true for every single CSP, that there's some notion of bias, which is the optimal thing you can compute for it in like polylog n space. And if you want to beat that approximation, you have to go to like square root of n space. So that's why this is interesting. So let me quickly go over what the approximability curve is. So if this was the curve that we saw before, where we had this lower bound and upper bound on Max-DICUT value in terms of bias. And now if I plot it as an approximability curve, where I have, again, beta on the x-axis, gamma on the y-axis, it looks something like this. And what we do is that for this entire range of beta and corresponding gamma, we create instances such that the one side instances match this value, and another side the instances have Max-DICUT value this, but they're inseparable in the streaming, indistinguishable in the streaming segment. So let's see how that goes. So for streaming lower bounds, we typically use lower bounds from communication complexity. And in this case, we use this problem called distributional Boolean hidden partition. So we use the hardness of this communication game to obtain a reduction to show that computing Max-DICUT is also hard in the streaming setting. Okay, so let's have a high-level view of what this problem is. So this is a game where you have two kinds of instances, and there are two players, Alice and Bob. They don't know which instance they have, and they have to, using some minimal communication, be able to tell one instance from the other. So in the yes case, Alice gets some random partition of a graph, and Bob gets union of some sparse random bipartite graphs respecting this particular partition. So Bob doesn't have any idea what the partition is. All he sees are just some random edges. And the promise is that in one case, the edges are going to like respect the partition. And in another case, again, Alice gets the same random partition, but Bob is going to get some sparse random graph, something that doesn't have to respect any partition information or something. The idea is that, so you want to distinguish between these two cases, let's say with some good constant probability. Now, but by the birthday paradox, you can actually solve this problem in like order root and bits of communication. So the goal is like Alice has to send some bits to Bob, and then Bob has to output whether or not their inputs are in the yes case or the no case. So if Alice sends some square root of n random bits from her thing saying this vertex is placed in the left side or this vertex is in the place in the right side, like information like that, then Bob can use it to actually determine which case he's in, whether he has a sparse random bipartite graph or just a random graph. Now, it turns out that this is actually optimal strategy in the sense that omega square root of n bits, in fact, is necessary to distinguish between these two cases. And these works essentially show that. So now what we'll do is that we will use this communication problem and reduce it to the Max-DICUT problem for this entire range of like gamma and beta that we saw in the approximability curve before. Precisely this. So we show that for this entire range. In the yes case, we reduce the instance that Alice and Bob get to some instance with Max-DICUT value at least gamma, and in the no case, it's reduced to an instance with Max-DICUT value at least beta. Okay, so how does the reduction work? So assume that they have like a algorithm, streaming algorithm that can solve the Max-DICUT problem. What Bob does is that, so when it hit, so the idea is that Alice adds some edges to the portion of the stream, and Bob later adds some edges to the portion of the stream. They run the streaming algorithm together and then use that to determine whether or not the Max-DICUT value is in which interval that it belongs to. So let me just first describe the edges that Bob does. So because Bob doesn't really have any information a priori about like where the vertices are placed and stuff. What Bob does is just simply for every undirected edge he has, he adds two directed edges, like one going in either direction. So Bob's reduction is pretty simple. What Alice does is something interesting. So what we want to do is like create instances of like bias B. And definitely Bob cannot do this because Bob actually doesn't have any idea about what the partition is. So what Alice does is like, let's say that the total number of edges that Bob is going to create is M, then Alice adds some proportionally so many edges from like, from this left side to the right side that she has, creating an instance of like bias B. And the idea is that in one case, in this yes case, when Bob has this bipartition, he is actually getting the yes case is Max-DICUT is at least gamma of B, and no case, it's beta of B. And this is actually easier to see in high bias regions because, for example, let's say we want to show that the no case Max-DICUT value is at most this, then it's like when bias B, little b, is really high, it's really Alice's edges that dominate the Max-DICUT value. And so this turns out to be the optimal partition, which is why in this case, like Max-DICUT value is same as beta of B, which was this B itself. So that's sort of the intuition, but yeah, so this is how the reduction works, and that's the separation. Okay. Any questions so far? Okay, now comes our most recent work where we show that this is, we can actually beat this, if just given a little more than square root of n space, you can beat the optimal 4/9 approximation that you saw before. And let's see how we do this. So the high-level idea is that you can sketch what is known as a snapshot of the graph in order square or O tilde square root of n space, and use this snapshot to compute something, to basically infer more information than what just looking at the bias vector of the graph would have given you. So, okay, what is this snapshot? So let's say this is your directed graph. Snapshot is something where you collapse vertices of the same bias into one big bubble and basically treat them all as like the same vertex or something. So in this case, like vertex 1 and 2 have the same bias, and so you collapse them. and look at this sort of like a collapse graph, which is what we call a snapshot. And the idea is that we can, like, from this snapshot, you can get better approximation, and the snapshot itself can be estimated in ordered like square root of n space. That's sort of the high level idea. And why are these snapshots enough? So there is this interesting work of like Feige and Joseph that study so-called oblivious algorithms for Max-DICUT in the classical setting. So what are these algorithms? So they want to study those algorithms which are indifferent between vertices of the same bias. Basically, these algorithms, you can think about them as like having only the snapshot as the input. They don't see anything more about the graph than the snapshot, and they really have to treat like every vertex of the same bias in a similar way. So they study these so-called oblivious algorithms, and essentially they show that you can have these selection functions which have these constant many like bias intervals, such that if you use, what is the selection function doing? It is partitioning the entire bias range. One more thing, I'm actually normalizing this bias. I should have mentioned this before. So you take the out degree minus in degree and also divide by the degree. So bias is actually in the range like -1 to 1. So you look at all the vertices in this range and partition the biases into various intervals. And for every vertex that has bias in a particular interval, you place it in left set with probability whatever p0 here, and right set with probability 1 minus p0. So you sort of treat all the vertices not just in like same bias, but within the same bias interval the same way. So that's what a selection function is. And they give us selection function which has like just constant many intervals, and it achieves like 0.483, which is bigger than 490 approximation. And they also give a lower bound that shows that you cannot, that there's no oblivious algorithm that can actually beat 0.4899 approximation. I mentioned this here because if the truth is that you can actually achieve half approximation in square root of n space for Max-DICUT, then this is not the way to go about it, because their lower bound shows that using these so-called oblivious algorithms, you cannot really push beyond 0.4899 approximation. So that's another interesting thing. At the moment, we do not know if in square root of n space, these snapshot computation is the optimal thing we can do. So that would be another like a very interesting thing to figure out. For streaming algorithms, what's the best you can do in square root of n space when it comes to approximating CSPs? All right, now to the actual, yes.
So this graph that you're creating has constant size, no? The snapshot?
No, it doesn't have okay.
If you discretize it in one bus.
It has constant size, yes. Yeah.
Then if you find the best max cut of that graph, is that the 0.4899?
I don't think so. So that's a good question. No, I don't think so. No, not the snapshot. If you just compute the Max-DICUT value of the snapshot, that doesn't give you a good approximation. Yeah, it doesn't. Yeah. Snapshot just helps you compute like all these. Yeah, basically you have to do this. No, yeah, snapshot doesn't give you.
By the number of vertices in each process, you probably have to weight it.
Yes, you probably have to weight it, but good question.
I think the Joseph thing gives you like explicit probabilities that you're supposed to do for each pair of classes, if I remember correctly.
But that's algorithmic. Here you don't care about runtime. You have this constant thing you can brute force through it.
I don't know.
So this means that every class can be split. I think so.
Okay, yeah, I'll get back to you at the end of the Yeah, thanks. Okay, so let's talk about how we even estimate this snapshot in streaming model. So first, we can assume without loss of generality that the graph itself is sparse, because you just subsample and you can get 1 minus epsilon approximation. So we might as well assume the input graph is sparse. Now, let's actually talk about the random ordering algorithm, which is quite simple. So you just take the first order 1 edges and store the induced subgraph and track the biases of the vertices, this helps you compute the snapshot, because you just need this constant, as Safir pointed out, the snapshot itself is of like constant size, and then you just need constant many edges to estimate the snapshot itself. And if you're doing 2 passes, then again, it's like a straightforward extension from this algorithm, because you just use the first pass to sample constant many random edges. And the second pass, you basically do this whole thing of storing the induced subgraph and tracking the bias of the vertices. So the algorithm is actually quite simple when it comes to like random ordering and 2 passes. And even for bounded degree graphs, so the idea is that we want to actually get random edges, but in adversarial ordering, you don't have random edges. And the closest thing you can do is actually sample random vertices and look at the induced subgraph. And if you hope is that if you sample enough number of random vertices, then you can apply concentration bounds to approximate this snapshot well. And it turns out that if you're looking at bounded degree graphs, square root of n vertices suffices. So far, all good, simple. But bounded degree assumption is really crucial for this algorithm, because let's say I have the star graph. I mean, it could have a Max-DICUT value 1. And if I'm just going to sample square root of n random vertices, I'm not likely to see this middle vertex. So when I like track just the induced subgraph on that on the sampled vertices, I'm not going to be able to see this middle vertex itself, and that's not going to give me enough information about what the Max-DICUT value is. So we do something more intricate for arbitrary graphs. So we do this thing called layered sampling of vertices, where in our final graph, we want to see like some kind of uniform sample from every degree class or something. So what we do is like we partition the entire degree range into log n many intervals, and then we try to get a uniform sample of vertices in each degree interval and store the induced subgraph there. So the idea is that we want to sample, let's say, vertices of degree d with probability d over square root of n. So for vertices with degree higher than square root of n, you just basically end up storing all of them. And for other vertices, it's like d over square root of n. You can check that this still makes sure that the space is only like upper bounded by square root of n, and they still have factors. But of course, the challenge is that when you see a vertex, you have no idea what the degree of the vertex is. So it's not that I can look at the vertex and say, oh, hey, it belongs to this interval. Let me sample it with this probability d over square root of n and place it or something. So that's the challenge, first challenge, that we do not know the degree of the vertex when it first appears. So we do something else. We actually do a layered sampling of the edges and use that to sample vertices. For example, let's say that I look at my graph and subsample edges with probability 1 over d. Then first of all, you're only likely to see in this new graph, or the edges are going to be incident only on vertices which have degree at least d in the original graph. And there also you expect them to have degree roughly order 1 in the subsample graph. So the idea is that you look at first you subsample edges, and then subsample vertices with the desired probability. Ignore those vertices which have degree like much larger than constant or much more smaller, and you're not even likely to see many such vertices which have like degree much less than constant. And okay, any questions? And what is the issue here? So you can still misclassify vertices, especially those at the boundaries of the degree intervals, and place them either in the left interval or in the right interval by mistake. You could also potentially make errors in bias computation. If you looked at the previous algorithms, like you just sampled a random edges or random vertices, you knew beforehand which kind of vertices you're going to be keeping track of. So you actually compute the biases exactly. So in the snapshot estimation, you don't make any mistake in the bias computation itself. Here you could also mess that up if they are in the boundary. The vertices could be placed in the left interval or the right interval, even in the biases. So you could have such issues as well. So how we handle that is by doing some smooth estimate of the snapshots. So what's a refined snapshot is just that originally our question was like, how many edges go from some bias interval to another bias interval? Now we also like do this fine-grained thing of like bias interval bi, some degree interval dj to bias interval bk, and like some degree interval dl or something. So this is just a more refined notion. If I just like want to compute from bias interval bi to bk, I just sum over all the degrees. So I can still get the original snapshot I want from this refined snapshot. Now, what is the smooth snapshot? We look at the average of these entries of this matrix over a window of size w.
Question. This is still something buffering in the previous slide. So how big is D? Because like if D is less than then say you have a matching, you would have these spurious vertices. You always get MIT edges, right? And these are vertices of degree 1, right? But you still can look at story edges. How do you filter them up?
So wait, so what do you say? Does it also apply to like their degrees being log n or something?
I guess if you just go back to the previous slide.
Sorry.
No, again. Forward from the one with D sample, the one with D sample. The edge sample.
Oh, the edges.
Yes, yes.
Okay.
Yes, if you say that you ignore the issues with really much bigger than above log n and much smaller than above log n,
Right.
how much space will the thing take as a function of D?
Overall, it takes square root of n space. Okay.
Say D is 1 over n to the quarter.
Okay.
Just take a sample of edges with probability 1 over n to the quarter. Say if the graph is just matching, we'll still look at n to the 3 quarters edges. We should technically ignore all of these vertices.
She's only storing them on the 10 vertices.
Oh, it's in a subset of the
Yeah. Oh, yeah, I'm not storing all of them. Yeah, sorry, I should have been clearer. Yeah, I'm not storing the whole graph. Yeah. Yes, I further subsample them and store only the subsample. Yes. Thanks, great question. Yeah. Okay. Okay, so we do this because it's you could actually make, if you're trying to compute the refined snapshot itself and get a pointwise good estimate of it, you're not going to be able to actually get it, because with high probability, you're going to make errors misclassifying these degrees and biases. So we ask for like a weaker thing where I'm only looking at like an average of this entry over a window of size W. In this case, let's say window of size 1, in the sense that I don't care if you misclassify things up to like 1, because I'm taking this average, just give me this average correctly. And if you take larger and larger window sizes, the boundaries shouldn't hurt you much because you're taking the average. So that's sort of the idea, that you can compute this smooth snapshot efficiently, and you should get better and better estimates as you increase the window size. Then, but then the question is like, how is this helping you? For example, if I take like very, very big window sizes, I'm not going to even like resemble this refined snapshot in any way. So from the smooth snapshot, I mean, if I'm taking just the average of all the entries in the matrix, I'm just going to get like value 1 or something, and that's not giving you any information. So this thing is like you have to hit the right balance. Like you cannot have very large window size. At the same time, if you have too small of a window size also, you get bad estimates. So sort of you are able to hit the right thing, and you get the correct thing that helps you approximate this refined snapshot. The question is like, why do these smooth snapshot even suffice? How do we get information about the refined snapshot from it? Basically, the question is, why don't misclassification errors matter in this sense? So if you notice that degree misclassification errors do not actually affect snapshot computation. This is because, let's say there is no error in the bias computation, but there's only error in the degree computation. Ultimately, you're going to look at your snapshot, sum over all the degrees anyway, and then compute the actual snapshot. So it doesn't matter if you actually misclassify the degrees. So we don't have to, this is why we don't have to actually compute the refined snapshot itself. Just computing the smooth version is enough. Whether you sum over the smooth version or you sum over the refined version, degree misclassifications are not going to hurt you. You're going to get the same value. Now, bias misclassification errors do not affect Max-DICUT value when the window size is small. This is because what does bias misclassification error mean? Like instead of like declaring your value of the bias as B, you're like declaring it as B plus or minus epsilon. So what happens is that a vertex, you can think about it as like perturbed in the sense that instead of you seeing it as a bias B vertex, you look at it as a bias B plus or minus epsilon vertex. Now, the idea is that you are able to perturb the original graph to get a new graph with similar DICUT value, such that if you look at the smooth snapshot of G, it corresponds to a refined snapshot of this new graph H. So in that sense, you're trying to estimate like the Max-DICUT value based on the smooth snapshot. And you might as well think about it as estimate the input being H and estimating the Max-DICUT value of this refined snapshot. So because the algorithm works on refined snapshot, it should also give you, within plus minus epsilon errors, the approximation for the smooth snapshot. And the idea is very simple. If the bias is off by epsilon, you just create a new isolated vertex and modify this bias by creating at most epsilon d new edges. And overall, this shouldn't change your Max-DICUT value by more than epsilon m. So your Max-DICUT value isn't changing by more than epsilon fraction. And that's kind of the idea. How many minutes do I have? Do I have time to talk about? 14 minutes? Okay, great. So maybe I'll also talk about generalizations to arbitrary CSPs, because hopefully this will motivate why we even want to understand the Max-DICUT picture in more detail, and hopefully that will also help us understand CSPs as a whole. In this case, I'll talk about our dichotomy theorem for arbitrary CSPs in the space of like polylog n versus like square root of n. So this is like a generalization for CSPs where we show that there is this general notion of bias, which you can use to like do this log n approximation for general CSPs or any sketching algorithm. So our bound is weaker here. We do not prove a lower bound against streaming algorithms. All we show is that if you have a sketching algorithm, then that cannot distinguish between instances that cannot be distinguished by bias, essentially. And at a very high level, the dichotomy theorem looks like this, where corresponding to every gamma beta, we define these convex sets, which we call like gamma beta sets. And if these sets are like separated, then bias can actually distinguish between gamma instances from beta instances. And if not, we show that you cannot distinguish them in like little or square root of n space. And to note that these are like actually convex, closed, and bounded sets in some finite dimensional space. And so this is actually a decidable condition. You give me a gamma beta and the truth table for the function for the CSP, then I can tell you in P space whether or not these things are separated, or there is some lower bound showing that these instances cannot be separated. That's like a very high level view of a dichotomy theorem. And I'll talk a little bit about like the structure of the bias. So you can look at the bias of the Max-DICUT graphs, and you can like rewrite them this way, where think of this as a bias matrix where it captures like the marginal information about every vertex. Basically, it captures the out degree and in degree of every vertex. And this is the expression for the bias, where you're asking for the like the L1 norm of the differences between the in degrees and out degrees. We can think about these as like some sort of weights, and this is computing like sort of how important like each coordinate is and how you have to assign your values. Now, the idea is that for at least Boolean CSPs, when you have like gamma beta that are distinguishable, you can choose a suitable set of weights instead of like 1 minus 1. This bias matrix still just says that how many constraints are there with, let's say, variable xj in the ith position. And so that is just like a generalization of this bias matrix you see here. And this weights just tells you like roughly how important each coordinate is. And the bias is again the same thing, where you're computing the L1 norm of this whole quantity. And this turns out to be the general bias notion that helps us like distinguish distinguishable gamma beta instances. And even for arbitrary CSPs, we have even more general notion. So it's like a very, very, very high level look of like how does this bias work. So we defined some yellow and red sets before and said that when they are separated, you can use bias to distinguish the instances, else you cannot. So thing is that these yellow and blue sets, red sets are defined in the following way. If your optimum, so these are in k-dimensional space, where k is the arity of the constraint satisfaction problem. And if the optimum value of your instance is at least gamma, then there exists some assignment A such that this quantity that you see here, BA transpose, is in the yellow set. And if optimum is at most beta, for every assignment, BA transpose is in the red set. So this is how these things are defined. And now when you look at, let's say that lambda corresponds to the normal of the separating hyperplane, if these two sets are actually do not intersect, then if you look at this quantity, which is like max of, inner product of lambda, gamma, beta with BA transpose, in one case, it should give you bias that at least, which is what I call the bias. One case, this inner product should be at least tau because of the separating hyperplane theorem. And another case, this should be at most tau because every assignment, this BA transpose is in this red set. Does it make sense? So yeah. And what happens when they intersect? When they intersect, it's the same idea as what we had previously for the Max-DICUT, in the sense that you can create two instances with the same bias matrix. And we show that when you have two instances from this region like gamma and beta, such that their bias matrices exactly match, then there is nothing you can do in the streaming setting, and you can't separate them in square root of n space. Again, lower bounds follow from hardness of communication groups. And the nice thing about these lower bounds in streaming is that they're unconditional because they follow from information theoretic hardness. Okay, so that sort of concludes my talk and some open questions. I think the most interesting question for Max-DICUT now is just understanding if we can achieve half approximation in like sublinear space, random ordering, multiple setting, whatever, like whether we can like actually get to this best half. And the next question is that now we have, can we have dichotomy theorems in sublinear space? For example, are first order snapshots actually optimal in square root of n space? This would mean that you cannot achieve half approximation in square root of n space, but maybe you can still achieve it in sublinear space. And if first order snapshots are actually optimal, can we also like generalize this to other CSPs and show something like even for them, there's some general notion of first order snapshot that can be used to get the optimal approximability in this space. But that's about it. Thanks a lot for your attention. Thank you.
Questions for Santhoshini?
Thank you very much. Just one quick question. I just want to understand the bias in the arbitrary CSP's definition. For example, the CSP, you had that, let's say the last, let's say we have three arity3 constraints, and we want the last, like the example you showed, the last vertex to be yellow or something. How would the, and I give you some sort of graph on top of that, how would the bias look like in this example?
Oh, that's a good question. Thanks. So one thing I didn't, I sort of skimmed over is that when I define bias here, I assume that I only have like one type of constraint. So if you're
one type of
constraint, if you have more constraint, then you have like another dimension there for like a layer of, you can think of it as a tensor. For every constraint, every type of constraint, you have like a bias matrix that you have, and so it's like a tensor. But yeah, in your question, if you just have one type of constraint, I can forget that because it's the same constraint that's applied on all sets of variables. So all I ask for is like how many constraints are there with my variable, let's say xj, in this particular position,
okay,
and that's all this information.
But
that's just sorry, I should have made it clear. I'm assuming in this definition that it's just like one type of constraint.
Okay, thanks.
Thanks. Good question.
More questions for Santhoshini?
Just to not get the image of the separating hyperplane correctly. So in this space, like, what are the vectors which I would, for instance, think about as being like orthogonal on one side or other side of the hyperplane? Like, what do I check against? So that makes sense.
Let me see.
So yeah, we have.
This is the thing. Yes. So are you talking about vectors what
So-
these vectors are in this space, or
Yeah. So for instance, you said like in P space, we're able of like distinguishing which case we're in or something like this, right? And so
okay.
we're like, there's some notion of like, there's these vectors which we can like computationally compare against, and what is the space of these vectors are we looking at?
So that's a very good question. Thanks. So it actually looks like you can, whether these two sets intersect or not, can be actually expressed like in the quantified theory of reals. You can say something like there exists blah for all such that this polynomial has some root or something like that, and which is why like you can actually like do it in P space. So
Okay.
the actual definition is a little more intricate. I'll be happy to take it offline, but
Okay.
but
Gotcha.
the reason why it's P space, because just the question of whether these two sets, which I haven't even defined, which is why it's a little hard to explain what I mean, but this decidability criterion can be expressed using this quantified theory of reals, which is just a bunch of quantifiers and asking whether some polynomial has a root or not, and then that itself can be computed in P space.
Cool. Thank you.
Okay, thanks.
I have a question about like the dependence on the bias. So if the bias is 0, like if your graph is essentially undirected, then you get back automatically to this like 0.5 approximation.
Correct.
Because you just don't need to even estimate the bias.
Perfect. Yes.
And then like your lower bounds, do they hold even when the like in the instances of the lower bounds, do they hold, does the bias need to be quite large, like some constant, or like it's
Oh, it holds. Yeah, that's a very good question. Thanks. But it holds in the entire range, because if bias is 0, what happens is that Alice doesn't even add any edges, right?
right?
So then in one case, you have this random directed graph, which gives you 1/4 approximation. In another case, you have a random bipartite graph, but edges going in both direction, which gives you Max-DICUT value half.
Right.
Even those are inseparable. So even when bias is 0 for the special case you asked, we give a lower bound that you cannot do better than half approximation.
Right.
Just by reduction.
But I guess what I mean then is like, so if bias is 0.001 or something, then your lower bound would be like 0.499. But you have this lower bound, you had this general lower bound of like 0.48 for this, for less than root n, right? Or was I confused?
Right. So, okay, let me.
Like, does that require the bias to be large? Or?
So the lower bound itself works in the entire range of bias. So this is this the slide that you're referring to?
Yeah, maybe.
Yes. So for this entire range of bias, you can see that, okay, so if we sit and compute what the Max-DICUT value of this distribution is, for smaller b, it's like, so this no value is the weirder thing. Like here, you're going to have, you just have to give one good partition, which turns out to be this like planted partition itself, which gives you this Max-DICUT value always like matching this curve, which is not
I see.
hard.
Okay.
But for here, it's kind of intricate in the sense that when bias is big, this is the partition that dominates. Like this turns out to be the best partition, which is why your graph looks like this. But when bias is like tiny, like this is not the optimal partition. You actually have to like look at like sort of a random partition, and that sort of gives you this like curve that you see here.
Yeah, I
So-
see. Okay.
So yes, you get it in the entire range that they match. Like
Yeah.
they just matches that and no matches that. It's just a little bit more intricate in the low bias region, but it's just basically computing the Max-DICUT value of this.
Okay.
Yeah.
I get it. Yeah. Thanks.
Thanks.
So in the random order setting for 1 minus epsilon and exact, are the current known lower bounds like just the same as the 1/2? Like, is there anything better than that?
Yeah, right now I think for random ordering, I mean, the best known lower bound officially, I should also talk to like Michael about it. Just had this conversation. So official known lower bound is like square root of n space. You cannot do better than half, but definitely Michael believes that you can do like even in little of n space, you shouldn't be able to do better than half by combining the techniques from adversarial ordering and the other square root of n space lower bound for random ordering. I haven't verified it, but I believe. So if you want to do 1 minus epsilon approximation, belief is that you might have to go beyond n space, which is anyway, even in the adversarial ordering, you know how to do 1 minus epsilon. So So yeah, I mean, so for random ordering, at least like the goal now would be to get to this half approximation, which would be very nice.
Thank you.
Any more questions for Santhoshini? If not, then let's thank her one more time.
Thank you so much.